Hello and welcome to my presentation. My name is David Romero and I work at the Universidad Politécnica Salesiana in the Robotic Integration and Automation Research Group. And now I'm going to present my work that is called On the Use of Phonotactic Vector Representations with FastText for Language Identification. To identify a language in a speech sample, we usually use two types of features. The first of them are acoustic features, where we use information of the audio wave, and on the other hand we use phonetic features where we use a phoneme recognizer to identify the phonemes of the voice wave. And in this way we use the information of these units to identify a language in a speech sample. Even though in this work we only use phonetic features, we also use an acoustic system to make a fusion of both systems and improve our results. So when we use a system to identify a language in a speech sample that uses phonemes as features, we face a lot of challenges. One of those challenges is that phonemes don't have the type of relationships that we have, for example, at the word level. Being those type of relationships so useful to solve this kind of problem. So to face this, we have created new units that are called phonograms, that are new units that concatenate two or more phonemes in just one unit. And in this way, we are introducing those relationships in these units. However, in this way, we are creating a lot of combinations, a lot of phoneme combinations, and increasing the variability as well as dispersion in our database. In this way, the system will face a lot of phonograms that did not arise during training, causing these units to be ignored or represented in an efficient way. So, for these reasons, in this work, we focus on representing these units in a better and efficient way for the lead task. So we focus on the main idea that phonograms could follow rules on its structure. So using the information of lower order n-grams could improve the representation of these units. Also that when the system faces new units during evaluation, for example, the system will use the information of lower order n-grams that learned during training to make the representation of these new units. So we make this using FastText, that is a library developed by Facebook to learn these embeddings using information. So in this way, we are using the morphology of the phonogram to make better representations for this task. So for our experiments, we use a database that is called Calaca, where we have a training set, a development set, and an evaluation set with 6 types of languages, where we have Basque, Catalan, English, Galician, Portuguese, and Spanish. So to make our experiments, we use this architecture that is divided into 2 parts. Firstly, we have the front end, and second, we have the back end. Each of these parts will be presented in a more detailed way in the following sections. So firstly, we have the front end. This part uses a phoneme recognizer to obtain the phoneme sequences of the speech audio. In our work, we have used a phoneme recognizer that was designed by Brno University, which has 3 types of recognizers for Hungarian, Russian, and Czech, with 61, 46, and 52 phones in each case. In this work, we have only used one type of recognizer, that is the Hungarian recognizer, which is the recognizer that has given us the best results in previous works. So once we have obtained the phoneme sequences, we create the phonogram concatenating the phonemes that were obtained by the phoneme recognizer. And once we have the phonogram, we represent this unit as a bag of words of n-grams. So in this way, we use these low order n-grams and the original phonogram to make the embedding that represent this unit. So FastText also uses special symbols to distinguish between prefixes and suffixes in each unit to make the presentation much more efficient. So in our experiments, we have considered two phonogram sizes, we have used a phonogram formed by the union of two phonemes and three phonemes, using 1 gram and 2 grams as sub information respectively. Then we have used the following parameters to train FastText, which are the optimal parameters for our system. So once we have obtained the phonogram representations, we replace each phonogram by its corresponding embedding. So here we have a set of embeddings representing each phonogram. So we use this set of embeddings to train an vector system, training the UVM and the T-matrix to obtain the I-vectors, where each I-vector here represents the corresponding audio of our database. So then we use the I-vectors that we have obtained by for each audio as input to a classifier to identify the language of the speech sample. So the metric that we have used is the average decision cost function. That is a metric that takes into account the false positives and false negatives obtained by the system. So we have used the following parameters with a plenty close condition. So as baseline, we have used the same architecture of our system, but instead of FastText, we have used SkipRAM. With SkipRAM, we don't use information to learn the embedding. So to represent phonograms that are not present in the training set, we represent those units as embeddings of low values. On the other hand, with FastText, we use the information of lower order units that were learned during training to make the representation of the phonogram. So in this table, we show our results where we have the C-average values for each language using phonograms formed by the concatenation of 3 phonemes and 2 phonemes. So here we can see that all of the results obtained with a system that uses FastText are better than the results obtained using SkipRAM, where we can see an improvement on each language. After this, we have done the fusion of the results of each language to obtain the final performance, where we can see here more clearly that the results obtained with FastText are better than the results obtained with SkipRAM. In this case, we obtain a better performance using the phonograms formed by the concatenation of 3 phonemes than the results obtained with the phonogram formed by the concatenation of 2 phonemes. So once we have obtained our phonotactic system, we fusion these results with an acoustic system. We have used an acoustic system that has been obtained as follows. So firstly, we have used male frequency substrate coefficients that are extracted for each frame. Then the silence and noisy segments have been removed using a voice activity detector. Also, a Rasta filter has been used along with substrate mean and variance normalization. We have used also SDC parameters and trained a UVM to extract the I vectors for the acoustic system. So in this table, we can see the results obtained by the acoustic system, where we have obtained a C average of 7.60. So after this, we have done the fusion with the phonotactic systems that use FastText and SkipRAM to learn the phonogram embeddings. So here we can see that the fusion of the acoustic system with the phonotactic system that uses FastText get a better performance than the system that uses SkipRAM. So in this case, we have obtained a better performance with the system that uses FastText and phonograms formed by the concatenation of 3 phonemes, where we get an improvement of 24.8 compared with the acoustic system alone. And with the phonogram formed by the concatenation of 2 phonemes, we have only obtained an improvement of 21.1 compared with the acoustic system, where we get a better performance with a phonogram with 3 phones. So as a conclusion, we can see that the proposed approach showed that the uses of information improve the phonogram embeddings. Also that despite the use of small units as sub information, these units provided useful information to to improve the representation of common and rare units. The representation of these new units or phonograms that have not been seen during training are represented more efficiently using subword information. So this has been shown in our results, where the system that uses FastText improves the performance of a system that only uses a skip without information to make the embeddings of each phonogram. So this has been my presentation. Thank you so much.